In this lesson, we will define the least common multiple of two positive integers and find a formula for the least common multiple that depends on the greatest common divisor of the two integers. The least common multiple of two positive integers A and B denoted LCM of A and B is the smallest positive integer that is a multiple of both A and B. So here's a couple of quick examples. The least common multiple of 3 and 5 would be 15. Notice that 3 and 5 are relatively prime, and so the least common multiple of any two relatively prime numbers would just be the product of the two numbers. The least common multiple of 6 and 21 is 42. So we don't need an algorithm to find the least common multiple because we already have the Euclidean algorithm for finding the greatest common divisor of A and B. And there's a nice little formula that we'll present in a few minutes that gives the least common multiple in terms of the greatest common divisor. But first we need to prove a couple of lemmas that we'll use to find our formula for the least common multiple. Just as a side note, I'm using the word lemma for this theorem because I'm going to use this to prove another theorem later. So lemma 1 says that if the greatest common divisor of A and B is D, then if I divide A and B by the greatest common divisor D, the result will be two relatively prime integers. In other words, the GCD of A divided by D and B divided by D equals 1. Let's give a proof of this. In order to show this, we will show that the only positive common divisor of these fractions is 1. Therefore, the greatest common divisor will be 1 as well. So let C be a positive common divisor of these two expressions. Then I can write A over D as a integer multiple of C. Let's say it equals C times M. And B over D equals c times some other integer, let's call it n. Okay. If I multiply both sides of these equations by d, I see that a equals cd times m, and I can write b as cd times n. And this proves that cd is a common divisor of both a and b. Well, since c is a positive integer, c is greater than or equal to 1. So if I multiply both sides of this equation by d, which is positive, I get cd is greater than or equal to d. But since d is the greatest common divisor of a and b, cd has to be less than or equal to d. So we have that cd is greater than or equal to d and less than or equal to d. Therefore, c must equal 1. And that finishes this lemma. Now the second lemma that we're going to use to prove a formula for the least common multiple. Let's call this lemma 2. So we have natural numbers a, b, and c. So these are positive integers. Then it's a fact that the least common multiple of CA and CB equals C times the least common multiple of A and B. So for positive integers, I can pull out a common divisor from the least common multiple of two positive integers. Okay, so here's the proof. So A, B, and C are natural numbers. Let's let M equal the least common multiple of CA and CB. Okay, and I'm going to let N equal C times the least common multiple of A and B. Okay, so we will show that M equals N. Well, since the least common multiple of A and B is a multiple of A and B, I can write the least common multiple of A and B as A times an integer, and I can write it as B times an integer. So the least common multiple of A and B equals A times some integer x, but it also equals B times some integer y. Then N, which we said equals C times the least common multiple of A and B will also equal C times AX, and it also equals C times BY. So N is actually a multiple of both CA and CB. Since M is the smallest multiple of CA and CB, we see that M is less than or equal to N. So since M equals the least common multiple of CA and CB, and N is a multiple of CA and CB, it must be true that M is less than or equal to N. Now I'm going to show that N is less than or equal to M, and we can conclude that M equals N. Now, the M, which is the least common multiple of CA and CB, I can write M as CA times some integer x and CB times some integer y, some xy, some integers x and y. Again, this is because M is a multiple of both CA and CB. Then M divided by C is an integer, AX, and it also equals BY. So MC is a multiple of A and B. Therefore, M over C is greater than or equal to the least common multiple of A and B. So the least common multiple of A and B, by definition of being least, it must be less than or equal to M over C. But multiplying both sides of this inequality by C gives C times the least common multiple of A over B less than or equal to M. That is, N is less than or equal to M. So I've shown that M is less than or equal to N, and I've shown that N is less than or equal to M. It must be true that N equals M. And that finishes the lemma. We will now use the previous two lemmas to prove a formula for the least common multiple. The least common multiple of A and B equals A times B divided by the greatest common divisor of A and B. So once you've done all the work using the Euclidean algorithm to find the greatest common divisor of A and B, you can quickly find the least common multiple of A and B. So let's let D stand for the greatest common divisor of A and B. Since D is a divisor of A and B, I can write A as D times some integer M, and I can write B as D times some integer N. Then the integer m equals a over the greatest common divisor of a, which is d, and n equals b divided by the greatest common divisor of b. But by lemma 1, m and n must be relatively prime. In other words, the greatest common divisor of m and n must equal 1. So by lemma 1, the greatest common divisor of m and n equals 1. So m and n only have one common positive divisor, namely 1. Since m and n have no positive common divisors other than 1, the smallest positive multiple of m and n has to be m times n. So the smallest positive multiple of m and n has to equal m times n. In other words, the least common multiple of m and n, which are relatively prime, equals m times n. Now we'll put this together to get our formula for the least common multiple of a and b. We're going to use lemma 2. So by lemma 2, the least common multiple of a and b, and I'm going to rewrite a and b as dm and dn. By lemma 2, I can factor out a d from inside this least common multiple. So by lemma 2, this equals d times the least common multiple of m and n. But since m and n are relatively prime, we saw that the least common multiple of m and n is m times n. So this just equals d times m times n. So this equals the formula in the theorem. Just to make it look exactly like the formula in the theorem, I'm going to add an extra factor of d to this expression, and I'm going to divide by d. Now this looks like, if I replace dm with a and I replace dn with b, this looks exactly like the formula that we required. ab divided by the greatest common divisor of a and b. So here's a quick example using this formula. Recall we used the Euclidean algorithm to find the greatest common divisor of 482 and 1180 equals 2. So now we can find the least common multiple of these two numbers. So the least common multiple of 482 and 1180 equals 482 times 1180 divided by their greatest common divisor, which is 2. This equals 284,380.